I guess we are recording. Yeah, okay. Hello all and welcome to the week 9 session, the last session for this Intro to ML course. So we'll try to quickly wrap up the week 8, questions and solutions. And then, any doubts that you have in general for whatever previous weeks content, we can go over that also, right? And let's try to keep it keep it brief. So if you don't have anything very substantial to add to the discussion, then feel free not to pitch in. Otherwise, if you have something which is very pressing, then we can discuss that in terms of the week 8 assignment. I'm telling. All right. Uh, all right, let's start with this first question. So what is true about k-means clustering? I guess all of the above is the right answer. It's sensitive to the cluster center initializations. Bad can lead to poor conversion speed and can also lead to bad overall clustering, right? Any doubts in this question? I guess this should be very clear from the lecture videos, right? Okay. Second question: in which of the following cases will k-means clustering fail to give good results? So again, yes, we know that k-means gets affected by outliers, mainly because we have this mean operation that we do, right? So mean is sensitive to outliers. Then data points with round shapes, it will be good for data points with round shapes, right? If you want more if you want a mathematical intuition of why this is true, you can look at, so I'm talking about question 2. If you want to know why it works good for round shapes, you need to look at this k-means as a special case of Gaussian mixture models. See, if you're not aware of these terms, leave it. In case you're aware, then you can just look at this particular thing. It's a very famous proof, right? You'll get it anywhere. If you look at that, you'll get a mathematical intuition of why this is true. All right. So that
Sir,
is,
when it says about round shapes, it means all the points together, they form a round shape in that one cluster. Is that right? Around when they say round shape.
yes, yes. So every cluster should be like round shapes, and the two and it should be like far apart. Then yes, but yeah, round shapes is what will be good for k-means clustering.
Okay.
Yeah. Data points with non-convex shapes, again, no, because B is true, so then C cannot be true. And with different densities, like, also again, no, right? For density-based things, you can use other different clustering algorithms. All right. Uh,
Why doesn't it work for the density based, sir, with different densities? If it is
um,
far apart, still those clusters are far apart.
right. This is the idea, right? So let's say when you have things like this, let's say very dense network here and then very sparse something like this. So even though they are different, what k-means will try to do is it'll try to make it'll try to it'll get affected by these points. Ideally, we want these to be different and these to be different, right? But because k-means has this roundness compulsion in it, so it won't work with this sort of with this sort of systems. So where points are separated with different densities among themselves. That's the reasoning again. So it works
Okay.
well only for the round shapes sort of argument.
So even for round shape means my question is might be both are round shape but both are of different density. Will that
Even
work?
even then it won't work. Correct. Yes, because again, so the idea is, let's say something like this, and you're saying like this, right?
Right, sir. Yes.
No. So it won't work that well because of the fact that this k-means tries to has a constraint that all the clusters should have the same variance across all directions. Now here the variance will be very less across directions, but whereas here it'll be more. So it won't give that good result as compared to any other algorithm, like for example GMM, for that example.
Okay.
Yeah. Right. Which of the following clustering algorithm suffers from the problem of convergence at local optima? Again, k-means and expectation maximization clustering algorithm. These two. So k-means is actually, oh sorry, not special because of GMM, but yeah, EM applied on GMM. So EM is the expectation maximization algorithm, and that is basically so both of them have this issue of local optima convergence. Like they won't go to global optima even if it exists, right? It's possible that they may not go there. Agglomerative clustering goes to global optima in case we have single linkage. So it's very specific use case, but it is shown that it can go to global optima also. Diverse clustering, I don't know, I don't think this exists. I guess this is some sort of a problem, typing mistake, but so A and C are the answers. So more details if you want. I think let the solution thing come out, where we, and then you can post your questions. Then we can discuss in more details. All right. Any more doubts on question number 3? All right. Question number 4. So in the figure below, if you draw horizontal line on y-axis for y equal to 2, what will be the number of clusters formed? Ideally, this should be straightforward. 2 clusters, right? So this will be one whole cluster. That is C, D, E, F will be one cluster, and AB will form another cluster, right? So basically, how many ever lines in this dendrogram it cuts, that will be the number of clusters it'll basically form, right? That is the B, answer B. Okay. Question number 5. Assume you want to cluster 7 observations into 3 clusters using K-means clustering algorithm. And after the first iteration, you have these 3 sort of clusters are formed, right? Now, what will be the cluster centroids if you want to proceed for the second iteration? Any thoughts? How will you compute the cluster centroids? So what are cluster centroids and how do you compute them in K-means clustering?
Mean of those points in that cluster, sir.
That's it, right? Mean of those points. So here it'll become 12 by 3, so 4 comma 4, and then 4 by 2, that's 2 by 2 comma 2, and 14 by 2 is 7 comma 7, right? So the answer is A. So 4 4 2 2 3, 7 7 are the cluster means, centroids or means. Then question 5: what is the Manhattan distance for observation 9 comma 9 from the cluster centroid 1?
Sorry, sir. Can you repeat number 5? Question number 5.
Question number 5.
Each of them mean of each of them, like C1 the mean,
right?
then
Just yeah.
C2. Okay.
C2 mean, C3 mean, and when you say mean, we are doing mean for per dimension. So it's X and Y, right? For example.
Okay.
So for X mean, for Y mean, that will be the mean cluster mean for that cluster. All right.
Okay. Thank you.
Then the Manhattan distance for the observation 9 comma 9 from the cluster centroid C1. So C1 cluster centroid is 4 comma 4. And we want the distance of that from 9 comma 9, but we want the Manhattan distance. So what is Manhattan distance? How will you compute this Manhattan distance?
This both the dimension absolute distance basically. So 9 minus 4, then again plus 9 minus 4, then it will be 10. I think 10. No?
10.
This is a equation basically.
That's it. Yeah. So Manhattan.
P is 1 actually. That was the idea.
P is 1, correct. So X, let's say Xi minus Yi summation, where I is the number of dimensions that we have. In this case, we have only 2 dimensions, X and Y, right? I don't want to use this one. So yeah, correct, fine, Y. So 2 points, right? So X and Y, each 2 dimensions. So we just have 9 minus 4 plus 9 minus 4, that is 10, right? So A is the answer. All right. Which of the following is not a clustering approach? So very clearly bagging, right? Because bagging we discussed last class, I think last week, that it's basically for your supervised algorithms, right? So it's not a clustering approach at all, where we use do get multiple subsets and all of that, right? All of these remaining are clustering approaches. Question number 8. So which of the following is correct? So first thing is obviously not correct, right? Complete linkage clustering is computationally cheaper than compared to single linkage. So how do you know it's not correct? Any thoughts?
Both the place is same because MN is because you have to from one cluster to all other clusters. We have to compare the distance. Then we are finding the complete means the maximum distance. Other one is the minimum distance, but total computation same.
No, no. So then what? So why is it computationally cheaper? So why is it computationally
It's not cheaper. It's not cheaper. So it is both the same complexity.
same complexity? No, no. But in your lecture notes, if you see, you have this one, right? What is the computational complexity for both the algorithms? Is it same? So where is that? Yeah. So single linkage can be done in order of n squared. But complete and average linkage is currently what algorithms we have, they do in order of n square log n, right? So complete is more computationally expensive than single linkage. Single linkage, I think, order of n square because you can do some sort of very sophisticated data structures you can use to
Sir,
compute this.
I have small doubt. See,
Go ahead.
complete average I can do it with the n square and log n. Whereas complete is actually almost similar to single. Only the which distance you are taking. That's only different. So how they are achieving? See, one ways I can be and by art, but the problem I'm single and complete only different is how you take the different. One is max, one is min. Really speaking.
Right.
Yeah. Then how it can be one space n square log n and one space only n square. Average is okay. Average is different methodology. Like we'll take the mean and whatever the so two again average two method is there. Whether I can merge and mean it or separate mean it. But this I understood. I didn't understood how the logic behind it, how the complete can be n square log n.
Okay. Let me check that and come back to you. Yeah. So you're right on that sense that I mean it's just for the sake. I mean just min and max. But what I'm assuming is even then the idea is that I think in single linkage you can use some sort of specialized data structures. So let me just check that and then I'll come back to you.
Okay,
Does that?
means for the shortest finding ke liye we can use some specialized approach. Whereas longer distance we can't do it. That may be the reason
Right.
behind it. Okay,
Right.
okay,
Right.
yeah, understood. Yeah.
So the minimum operation can be done, I think, a bit easier or whatever, like based on how you structure your data set and all of that. But anyway, let me just come back to that. Yeah, does that help? So yeah, that is that. Then single. So then the two is comparing k-means clustering and single linkage clustering. So any ideas why one versus the other? Like why is k-means clustering cheaper than single linkage according to the answer key at least?
So for k-means clustering, we don't compute that n square computation, and we don't do so. It is order of number of iterations into number of clusters into number of objects in that cluster and number of features.
So question 8, yeah. So k-means is order of this TKMN, if I'm not wrong, is what they use, right? And then order of n square is your single linkage clustering,
Yes, sir.
right? And here, yeah, T is a number of iterations that you want to do. K is the number of clusters that you have. N is the number of data points that you have, and M is what? One second.
Number of features for each data point.
Number of features, right? Number of features. right?
The M is given the object, N is feature. Okay, it doesn't matter. M or N doesn't matter. One is feature, one is the number of objects.
Right. So this is number of data points. So again, so I'm not completely sure here, but the idea being that this number is TKM. So basically, what does it mean when you compare these two, right? So for very large N, what will happen, right? So now for very large N, again, see, K will be very, K, you don't want very large at the end of the day, right? Because if you keep K very large, it'll just cluster each point as its own cluster. But we don't want to do that with K-means clustering, right? So ideally, idea being that this TKM number that you have will be not as large as N, right? Will not be as large as len, right? So therefore, this TKMN will be less than n square. Therefore, we say that K-means clustering can be computationally cheaper. But again, I'll not clear. So let's wait for the solution that comes out. Yeah, and there probably we can have much cleaner answer there. Does that help? So this is my understanding of why it should be computationally cheaper.
So, sir, here when order of n square, there it is not features, sir. N is not features in that single linkage. It is objects. So here, based on number of it is actually, if you compare with that symbols, it should be order of m square in single linkage. So if you use the same symbols, because here n is how many number of objects you have. So you kind of find the distance between that each objects with respect to other objects. So that is why it is very
points,
expensive.
Right?
Yeah, number of data points.
So n is number of data points, right? So here, here you're saying that m is the number of data points in this.
Yes, yeah, m is number of data points in this.
Okay. All right. Okay, sure. So let's wait for the solution PDF to come out. Hopefully, you should have much more clearer ideas there, right? Okay, got it. Dimensionality. Okay. Okay, next question is question 9. Yeah. So considering single linkage and complete linkage clustering, is it possible for a point to be closer to points in other clusters than to points in its own cluster? If so, in which approach will this tend to be observed? Any ideas why the last option is the right one? So we are saying that single linkage and complete linkage hierarchical clustering we have. And so let's say a point belongs to some cluster Ci, right? So what we're saying that there can exist some points such that this distance of this point from the points in this ith cluster is actually more than the point in some other cluster, right? Any thoughts why and how you would approach this problem?
At least single linkage, it is clear, sir. Might be in that single linkage clusters might be 2 points of other clusters might be close and all other points in that clusters might be far off. Then that minimum, if then the distance between two clusters is lesser than might be the intra cluster distance. So at least that we can visualize, but not sure of complete linkage, how that is there.
No, but we are not talking about between clusters though, right? I mean,
I think that is what is the question, right, sir? It is it possible for a point to be closer to points in other clusters than to points in its own cluster? So that is actually what it is.
So, okay, so to simplify matters, let's consider one-dimensional data points, right? One-dimensional points. So if you can prove it happens in one dimensional, then very easy to prove it will happen in high dimensionals, right? So let's say this is a line that we have, right? Now, so can you give me examples for single linkage where this can happen?
Not sure how means we have to draw that, sir. So might be let's put this point here. So let's put no, okay.
So let's say we have something like this, right? It's a one-dimensional, space. So how would you put points here to prove?
So might be for the cluster 1, we can put points at 1 we can put 1 point. At 2 we can put 1 more point, and at 5 we can put 1 more point. Okay, and cluster, yeah.
Okay.
So might be cluster 2 we can put 1 point at 6, 6, and then we can put the other points at 8 and 9 and 10. So that is cluster 2, 8, 9, 10. Or might be 8, 9. So we can just consider that, so that centroid is near. So this, I thought might be this is possible. 5 and 6 belong to separate clusters. They might be far off from their own and from the points in their own cluster, but might be near to the points in the other cluster.
No. So, 1 second. So, which is cluster 1 again? I'm not clear.
1, 2, 5.
1, 2, 5 is one cluster. Cluster 1.
Yeah.
Okay. And
6, 8, 9. Only 6, 8, 9. Yeah. Will not consider 10. Yeah.
Okay. No, but if this is the case, won't 5 and 6 become one cluster first? Why will 5 get clustered with point number 2 in single linkage?
Or let's consider there is no two units gap. Might be like only 3, 1. So one single line like that.
I'm sorry.
So if let's consider might be 5 instead of 5 and 6, we can consider 4 and 5.
4 and 5.
But might be, and in case if we have selected k is equal to 2, that is still possible, right, sir? If we select k is equal to 2, it also depends upon how many clusters we want.
No, but we're talking about hierarchical clustering, right?
Oh, okay,
so
okay, hierarchical.
Number of this one, right?
Okay, got it, sir.
So, so one example that at least I could come up with, and we'll discuss one point on that. So let's say if we have something at 1 and at 4, and then let's say at something 11 and 12, let's say. Okay, so now if you think about it, these two will become the first cluster, right? Because just 1 unit distance, and then these will become the first cluster, the next cluster, right? Because 4 is very far apart from these, all of this. So now we have 2 clusters. So I have, this is cluster C2, cluster C1. Now let's say consider a point which is like at this 7.1. All right, I have a point here. So if I use single linkage, ideally what will happen, this point is 3.1 units apart from this cluster C1, right? Because single linkage we're using, and it's different from C2 by a distance of, what is that called? 4. Sorry. How much? 11 minus 4, 3.9, right? So 3.9. So now what will end up happening? You will assign this point, this third point, to C1, right? So now the new, the new cluster that will be formed is this cluster, right? Now, if you see, the 7.1 point is actually far by 6.1 units from this one point in this, right? But it is closer to these two. If you see this point, 7.1 wala point, the distances are 3.9 and 4.9, whereas here the distance is 3.1, all right, but this is 6.1 with the point number 1, right? So therefore, it's like, so therefore this point is true. So now it is farther apart from one of the points in its own cluster compared to points in the other cluster, right? So this is one example where this single linkage, where this thing happens in a single linkage sort of scenario. Is this clear?
That last point, can you just tell, sir?
So what are we trying to, so what is the question asking? Is it possible for a point to be closer to points in other clusters than to points in its own cluster? Now see, the 7.1 wala jo point hai, that got clustered with C1, right? So now these three points are one cluster. So, but in the same cluster, this point is far from this 6.1, much farther than compared to the remaining the points in the different cluster, which is C2 cluster here.
Sir,
Right.
this is the impact of bigger become bigger. That was the impact of this one, am I right? The problem
I'm
with
sorry?
the single linkage. This is actually the result. There is one disadvantage of the single linkage. The bigger become more bigger.
Bigger become more bigger. Correct. Yes, because you just look at the shortest possible distance, so it can just keep growing very large. Yes, that is true.
And it large is the thin way, like thin. The other one, the complete linkage will go like a circular radial increase. This will be
Right.
like a line increase, like it will happen.
Right.
So this
Right.
is impact.
Yeah. Right.
So your idea basically, uh, the which is the neighbor of the link, the okay vertex, it should be the member of the one cluster is far from is placed far from the cluster, and it's very close to other cluster basically. That's what you are
Yes.
comparing 1 and 7 now. If you see the 1 and 7, the 7 is much far than 1, but it's very close to the other cluster 10 or 9 whatever.
Yes. Yes.
And this will happen in the complete also. If it is single, it is happening. If it's reverse complete also, it may happen.
Yes. So complete linkage also it can happen. And so one example, I think, so again, let's consider one dimensional system. So I think, yeah, so something like this, 1 and 3, and again, let's say 10 and 11 here. And then what we saw was, so let's say, so again, let's say complete linkage, right? So these two will get clustered first, and then these two will get clustered first. Now consider a point like 6.5, right? So now 6.5, so the distance from this, one is I think 5.5, right? 5.5 is this distance. And this distance will be, not this, right? So it will be somewhere here. So this is again going to be 11 minus 6, 5, 4.5, right? So it'll get clustered with this point, right? So this will become the new cluster. Right now, if you think about it, wait, I'm doing a mistake here. So you can have here 5 and 5, 6 closer to this. Wait, should I use?
If you take 4 also, it's okay. If the 1 and 3, if you take 1, 4, then 6.5 is very close to 4.
1 and 4, you're saying, is it?
If you take 1 and 4 also, it'll be same result. Now, 6.5 is very close to 4, but far from 10 and 11. No?
Far from 10 and 11, correct. And wait, but 1 second. Will they get clustered though? 1, 2, 3, and then 1, 2. No, if you use this one, 4 and 6 will get 4 and 6.5 will.
Yeah, it will be grouped.
That will be grouped first. So
Yes,
actually,
yes. No.
so what we can do is we can just shift this on the other side, I think. So we will get something like this then. So what we can do is take it to 11 and 12. Let's say something like this. I'm not sure if this works. Now it will be again 5.5. No. So if I use 6, then what will happen is it'll get clustered to this guy. And if I use 7, 6, and then 5, it It's far from this, but nearer to this one. Right, yeah. So if I use 7, for example, let's say. So what will end up happening is this will have 6 as your distance, right? It's in complete linkage. And this will have 5 as your distance in complete linkage. And this will become one cluster now, right? But it has a point in the other cluster, right? Which is closer to, for example, let's say from 7 to 6 is just 4 units, right? So it's closer to this compared to, let's say, a point that is 12, right? So, or I can do, can I do 7.5?
Or might be, sir, there might be 2 points, 6 and 7. So 7 will join 12, 11 and 12. 6 will join 1 and 3. And still 6 and 7 are closer, but still they are far off from the points in that other cluster.
6 and 7, but then if you do 6 and 7, then 6 and 7 will get clustered, no? That's the catch, right? You'll always have that. So
but sir,
from the
so initially 1 and 3 if they form, so afterwards every point would always check for that longest distance, right, sir? It will not go first and do 6 and 7. So might be 1 and 2, 1 and 3 is there, then it will check if for 6, if it is 1 and 3 will form first and 11 and 12 will form second, might be. And afterwards for 6 and 7 it tries to check for the other clusters, right? It will not try to form its own cluster.
No. Why not? Because I mean, how would you do complete linkage? You check for every possible cluster pair, right? At that time, since 6 and 7 are still not clustered, each of them is their own cluster. So 6 and 7, the distance is still 1. So actually, what will happen is 11, 12 can become first, 6 and 7 will become second, and then 1 and 3 will become, right? That's the complete linkage idea, no?
Okay, got it.
No, actually, I'm just explaining, sir. If there's a points are there, then it will be grouped with the shorter distance only. So since there's no point, if a point say 7, 8 is there, then 7 will be grouped first, not 1 and 3. Correct, no, sir?
Correct, exactly. So 6 and 7 will get grouped first, and 11, 12, and then let's say then 1, 3 will get grouped, right? All right. So I guess this is one example. So the idea, so how would you try to solve this is basically you can just look at like try to formulate it as a problem like this. Let's say D1 is the distance of the, let's say, some point P, right? Which we are trying to consider. So that's going to be the minimum distance, right, from the point P that we have under consideration, and let's say it's the cluster C1, let's say, right? Overall points in C1, right? Then D2 is again same thing, minimize over D, P comma C2. This is, I'm talking about for single linkage, right? So now let's say if D1 is less than D2, now because in C1 I can have n number of points, right? Let's say I call it like this. Let's say first cluster, first point, second cluster, first point, first cluster, second point, and so on. Same thing here. P1, second cluster, P2, second cluster, and so on. So now, let's say this is an ordered set. Okay, so the minimum distance that the point P has with this cluster 1 is with this P11 point. And the distance, so in the same way here, P12 is a point that which has a minimum distance with point P. So now what does it mean when D1 is less than D2? It means that your P11 point is nearest compared to P12 point. Now this P12 is less than P22 and so on, right? So the only ordering that we have is with respect to all these points. So now let's say the distance with this P21 point that is there, it can come here or it can come here, anywhere it can come, right? So therefore what will end up happening is you can have, it's possible to have a point which is, let's say, closer in this in the second cluster, but farther in the first cluster. Let's say P21 comes here in this way, Okay. See, if it's not clear, let's leave this for now. But I mean, the point is you can formulate it a bit more clearly. You'll get the idea why this is true. Why it can happen in both this single linkage and complete linkage. All right. We'll come back to this if we have time. Okay. But this is one way to solve this problem. Okay. Let's move on to the next question. Yeah, question number 10. Any thoughts why D could be the right answer? So what do we do in K-means clustering, by the way? Do we get something like this in K-means clustering?
No, sir.
Right, that's it. So that's the answer. So if you have if you do K-means clustering, you don't get something like a dendrogram sort of structure. You just get different clusters and done there, right? And do we have who was the last asked some question in the last section? Jitendra. So, did you get the answers to your questions? Last time you had some questions on this dendrogram, no?
Yes, I got it. Hello?
You got you got those answers that you were after?
Yes, it's
Okay.
clear.
Okay, great. Okay.
Sir, can you go to slides then?
Which this slide?
First slide only. There where dendrogram is there at the end. The slides, the class slides, sir.
Class slides.
Yeah. In there, dendrogram, the down.
Okay. This one?
No, come down, sir. Come down. Next. Wait, sir. Here. This one. Yeah.
Okay.
Here, that k is in reverse order, na? Supposed to be that k values. Can you see k equal to 1, k equal to 2?
No. Yeah, they are reversed. Yeah. No. This is not right. True.
Correct, na? I got
Yes. Yeah. So k equal to 1 means one cluster. So this is the point where you have one cluster because everything is in this one, and then we get two clusters. So sort of right. So you get this is one cluster, and then this becomes another cluster, and so on. Yeah.
It's in reverse order, correct, na, sir? Yeah.
Reverse. So I'm not sure why.
Why k is here? I got confused. Why k here? How? Okay, maybe. Okay, k is okay. It's not k means. The meaning is not k means. It is how many k values? Cluster basically.
Number of clusters. That's it.
That's okay. Given k is confusing basically, but it's number of clusters they're indicating actually.
Number of clusters.
But order as ulta. That's what I.
Correct.
Yeah. Okay.
That makes sense. Yes. Because then, so that's the idea, right? So each point is first considered its own cluster. So there are 8 points here, then k is equal to 8, and then as you build up, the number of clusters will reduce to 1.
Yes. Okay.
Yeah. Then feature scaling is important step before applying k-means. So this should be clear that in this calculation we get the same weights for all features, right? And again, so anywhere wherever you have distance calculations, just remember that feature scaling becomes a very important point, right? So even in machine learning, these sort of things start becoming a important sort of process to perform. All right. And B is not true, C is not true. Then which of the following the lecture slides also, RAND index, Jaccard index, and F score are all external measures of external evaluation measures. All right. So by the way, what is external evaluation and internal evaluation? Any thoughts?
External evaluation, we should have some labels so that we can compare that our prediction is coming, how much it is. Internal means only the values, what values are getting, how much deviation happened. So with that it is doing, whether it's Pearson water correlation you are using, with that values you are trying to do it, how much it is deviated. But this is external value. So suppose you don't have any label, we can't do external at all.
We can't do external evaluation, right? That's it. That's true. That's it. Yeah. So if external, you already have some ground truth with you, and you're comparing how good your so-called algorithm is with respect to that particular ground truth. All right.
Sir, one question here, sir. If we have external factor like labels, why do we even go for clustering in that case? We can go for some supervised algorithm only, right?
Correct. You can do that. One thought process is that to first of all to evaluate the clustering algorithm in the first place. See, because all this Davis-Baldwin index and all of those, let's say inertia measure, all of those. But so even if you do well there, how do you make sense that is it capturing the actual clusters in the data set or not? Right? That's the question. So having this external evaluation, external labels already present with you, then you can come to know, okay, is the clustering algorithm able to capture the patterns that you are hoping it to capture or not?
Sir, can I answer one more thing for this question?
Go ahead. Go ahead.
Sometimes it's better to do the clustering before doing the classification to make the optimization of the algorithm. For example, we have the huge data, like we know it's a animal pictures, human pictures, and the some other vehicle pictures. Okay, so which vehicle picture exactly or which animal picture exactly? That first we'll group it clustering. Once cluster is working, then you do the classification. Then algorithm very fast instead of directly going to the classification. Such case also this will be very useful.
Right. So you're so basically so that falls under sort of like a feature reduction technique in a way, right? Because then what you're doing is, I mean, ideally, the hope is then all of those points which you have, let's say animal faces or human faces that you were saying, let's say they fall under this individual clusters, then you can use those cluster centroids or some like measure of that cluster as an indicator of the label that you have, right? And then probably use that to classify your processes that you have, right? So that's one way of using it. It's right, Satish. That's fine.
In that case, I
Right.
have the
Thanks.
label data with me, so I can compare my clustering is done correctly. Then I go for the classification, very fast algorithm.
Right.
I think somewhere it's explained the class only. I think somewhere somebody, I think in the the TA is taking, that at the end of every class, that one class will be there. Practical. In that, I think it's explained. I think somewhere this approach.
Okay. That makes sense. Yeah. Does that answer your question,
Yes,
Bhavani?
yes, sir. Yeah, got it, sir. Even I could recollect once Satish was saying about that example. Yeah, thank you. Sir.
Okay. Question number 13, Jacquard index. Again, very straightforward stuff. Go ahead. Who is this?
Sir, sir, regarding exam, I have one question, sir.
Hi, go ahead, Abhi.
Sir, there will be any negative marking in questions or no? Something like that.
So again, so I've created a post on the discussion forum. So anything regarding final exam and all of that, you can ask there. I'm not aware of any of the details actually. So I don't know.
Okay, sir.
Yeah. Yeah. So question 13, very straightforward sort of idea. Just take the union and take the intersection and just compare the number of elements in those two sets. That will be that will be your Jacquard index, right? So you should get 0.33 as your answer. Right. Then let's say, yeah. Suppose you're running k-means algorithm on a
Sorry,
given
sir.
space.
Can you repeat question number 13? Sorry.
13 is it?
Yes, yes.
Yeah. So question 13. So let's say you have A and B sets are given to you, right? So Jacquard index, how do you calculate? Is just A intersection B by A union B. So take the intersection and the number of elements in that, then divide by, take the union and then elements in that number of elements. That's it. That's the Jacquard index.
Okay. Thank you.
Yeah. Then question 14. So suppose you run k-means on the given data set. What are the factors on which the final clusters depend? Again, very clearly, we know that all three affect your, what clusters do you get? The value of k, obviously. Then the initial cluster seeds chosen and the distance function used. So based upon what distance function you choose, different clusters will become more similar or dissimilar based on that also, right? So question 14, all three of them. Then question 15. Consider, so we have again same idea as question number, I guess, 11, right? So you have two features. Height is from 4 to 8, age is from 1 to 100. So before doing k-means clustering, ideally you want to do feature scaling, right? Because any measure of distance that you use, especially the Minkowski versions, they will all be affected by the value that is going into this one. So ideally, you would want to do feature scaling before you compare any distances between any points. All right. So A is the answer. So you want to do feature scaling before using k-means algorithm. All right. Any doubts on question on this assignment 8? I realize there are 2-3 questions here and there we have not covered in detail, and I've mentioned. I've also written to the NPTEL folks to send out the PDF as soon as possible, right? Before your exam dates are near.
Sir,
Anything?
question number 3, sir. You
Yeah.
mentioned. Sorry,
Yeah.
3. Okay. Where was okay? So you mentioned that for clustering, which the problem of convergence at local optima is for k-means and expectation maximum. But for agglomerative, you will have a global optima problem. Is that means? But global you'll always have a global optima. You'll not have a local optima. Is that what you're saying?
Yeah, so there is one condition where it goes through global optima. So exactly, I'm not really sure what else it'll come here. So let's wait for any detailed solution from the PDF side.
Okay. So means generally, if we think might be all hierarchical clusterings don't have a problem of local optima, convergence of local optima. Is that?
No. I wouldn't put it. I wouldn't put that blanket statement so loosely again. No. So
Okay.
yeah, agglomerative clustering also. What I've again very last minute sort of thing. What I've seen is that only for particular use cases it can go to global optima. So let's wait for the final answer because I'm not sure why it should be the other way around. Also, not really sure. We'll have to wait and see for this. Yeah. Yeah. Okay. So question. So this is the week 8. Assignment questions.
So for week 5, sir, you have replied in our discussion forum regarding 2 questions which were marked as 0 score. So the score is changed to 0. Let me see if what are those question 3 and question 10.
Okay. Let's go to question 3 and question. Yeah, I remember this. Question 3. Yes. Yeah. What happened?
Means if it's marked as 0 score, means couldn't understand, sir, why exactly it's marked 0 score and
yeah, so last time when we discussed the issue was the wording of the problem, right? So hard margin classifier doesn't allow any error, right? At least in the training side. So this low error is not right. So no error is the right answer. So hence we said, okay, this is a wording problem. So question number 3 is that. So hence this is given as a grace basically. So anyone who has given the right or whatever right or wrong answer is not considered here. Question number 10, again same idea, right? Because this sort of questions like what is commonly used, I'm not sure. I mean, we haven't even covered in the lecture videos anywhere. Commonly uses radial basis function, that is true, but it's not covered exactly in the videos. So we said that let's keep it as a grace.
Okay, so only because it's not covered, it's marked as 0 for question 10. Otherwise, the answer D is correct. Is that right, sir?
D is correct. Yes, RBF is commonly used in nonlinear classification tasks for SVM. That's true.
Okay, sir.
All right. Sorry, sir. Assignment number 7, question 3. Yes.
Assignment number 7.
Question 2. Question 2.
2. Yeah. So we have covered this, Ishan Hamza. So the right answer is 24, right? They have changed also now. So.
Okay, it's 4.
Yeah, it's D. We discussed this last time also. Okay. Any other questions?
Sir, assignment 3. Can you open the assignment solution?
Assignment 3 solution. Okay. Hmm.
The question number 4.
Question number 4. Yeah.
In
Go
the
ahead.
explanation, it is written that higher the value of k, the smoother is the decision boundary. But in question number 8,
Once again, what is the question? K is what? Oh, KNN. Okay. Huh. Higher the value of K, the smoother it will be.
so question number 8.
Question number 8. Okay.
In the explanation, it's written that higher value of k would lead to less smoothing. So I was confused.
No, but there are different things we're discussing, no? This is PCA, right? That is KNN.
Yes. Oh, yes. So, and seeing the graph, I couldn't identify that which one is smoother.
So again, see, we have, so this has already been discussed in the last assignments. I mean, all of the solutions have been discussed. I'm not sure why it is coming up again.
So I was absent. I couldn't attend that, so that's it.
No, we have the recordings, no?
Yes, yes.
So, I mean, I would suggest you, so again, take it as a general, idea here. See, we can discuss the same questions over and over. The idea of today's extra session was anything else that you need. So again, I would say question 4, KNN, which value is the highest, is it? So if you see here in this last one, see, because you have this point which are red is plus, right? So red plus are also getting classified as blue, right? So that's basically
Yes,
this taking a large neighborhood, right? Because around this is a large number of pluses, blue pluses. So hence it's getting classified as a blue point. And if you see here, there's a lot of fractures in the decision boundary, right? So that is when you have very small k. So that's the
yes,
process. Okay. All right.
Sir, for week 4, sir, just one quick clarification. Week 4 assignment question 7.
Week 4. Question 7, is it?
Yeah.
Go ahead.
So here, probability of k equal to 0 given a equal to 1, comma b equal to 1. So how we calculated in our class was, it's probability of a equal to 1, comma b equal to 1 given k equal to 0 into probability of k equal to 0 divided by probability of a equal to 1 into probability of b equal to 1. But my question here was, why are we not considering that the kind of joint like marginalization, sir? Because here c is also there, right? Because when I was trying to look at this question again, I was like thinking might be it should be like probability of k equal to 0 given a equal to 1, comma b equal to 1, comma for all values of c. But here it is not that. So why this one is different?
Okay. Yeah. So what are you saying? This has to be with C. How would you write this thing again?
So it is like probability of k equal to 0 given a equal to 1, comma b equal to 1, and for all values of c. So comma c equal to 0 plus probability of k equal to 0 given a equal to 1, comma b equal to 1, comma c equal to 1.
Okay, this exact question we discussed. I remember discussing this. So again, see, this is exactly what I was talking about. Marginalization and conditional joint. How do you work with this, right? So this is equal to probability of k equal to 0, c equal to, let's say, small c.
No, I don't know, might be if I've explained it. Okay, go ahead, sir.
So a equal to 1, b equal to 1. Then for all values of c, c equal to 0 and 1. This is equivalent. This is what we do. this is what is to be done, right? Because if you want to include a variable, you in this way you will just marginalize over that variable. Now you will apply the rule of conditionals, right? So now what will happen is you will get something like this: a equal to 1, b equal to 1, c equal to small c, let's say, into probability of c equal to c. I hope this is right. This is how you will do. So this is not equal to this. You'll also have a factor of this probability of c equal to c.
Right. And no. I think I just missed. I was always including that factor of probability of c, but this is how I calculated when I was doing it today. But it seems that was not how it was calculated, and the answer is different. So in our class, what we did was we ignored c. So what we did is we only did.
Correct.
We took it as like a Bayesian formula where we did probability of k equal to 0 given a equal to 1 comma b equal to 1 is equal to probability of a equal to 1 comma b equal to 1 given k equal to 0 into probability of k equal to 0 divided by probability of a equal to 1 into probability of b equal to 1. So this is what is the formula which we have discussed in the class. But why not the other one? No.
This is not, no. So this will have to be joint first. This has to be a equal to 1 comma b equal to 1. And then you will write this as again summation over k equal to 0 comma 1. And then you will write probability of a equal to 1, b equal to 1 comma k equal to k. Then you will again bring it out in this form. So you write probability of k equal to k given a equal to 1, b equal to 1 into probability of k equal to k. And apply. Oh, sorry, not this. Sorry, no. Conditional on the class. That's that I need. So probability of a equal to 1 comma b equal to 1 given k equal to k and then into probability of k equal to k. And then given the class, these two features are independent, and then you will multiply them. So it's not multiplication here, by the way. First of all, that is one thing. Okay. Second thing, you're saying what now? You want to write this as you want to use the c also in this. Okay. How would you use?
It is like for all c might be like the same thing. Whatever you have written there into probability of c equal to 0 plus that second line into probability of c equal to 1. So I was thinking of using like this.
This one you want to do it in that way.
Can I answer, sir?
No. So 1 second. So Bhavani, so where you want to include c in the denominator or in the numerator?
No. In the first line, sir. Not even here. So my formula was this. P of k equal to 0 given a equal to 1, b equal to 1, comma c equal to 0 into probability of c equal to 0 plus p of k equal to 0. So I was thinking of using this formula, but I didn't get the correct result. So might be I'm missing something here.
Wait, so this conditional I have to verify 1 second. So this will have to be. Satish, if you have something, go ahead. I think I need some time to think here.
I think, sir, this is explained. I think I don't know whether you explained or someone explained. It's clearly. I think if the water Bhavani told, no, that explanation will give more than one. Probability value will come more than one if you try that approach. Probability can't be more than one. So moment she try that approach, and for that the way you told, the first one, put the c in other side, k comma 0, c equal to c. That way should be the correct approach. And explanation they given, I think you given or other TA given, I don't remember, but it was there. Proper approach was given, justification was given actually. Why the other wrong?
No. So right. So I mean, one obvious, like one way of saying that, okay, the probability becomes more than one, but the question is why. I mean, what is the justification for that? No. Wait a minute. So this will have to be. Just give me a moment. So probability of AB given C. This is what we need actually. So we see probability of C. And I need in terms of A given BC, probability of C, no, BC, probability of C, BC into probability of B given C. Okay, I got it. The mistake is here. So this is the one. So This is not just probability of C equal to C, it's probability of A equal to C, C equal to C given B equal to 1, C equal to 1. This conditional will repeat here because of this formula, this way of writing things. Okay, so first thing, Bhavani, are the equations on this particular side clear?
Yes, sir. This is clear.
This is clear. Now, A, in our case, A is K equal to 0. B is that, C equal to C, small c they were writing. Capital C is basically that joint, A equal to 1, B equal to 1, right? Now, if I want to write this will become in this format. So it will become probability of K equal to 0 given BC, that is joint of these two. So A equal to 1, B equal to 1, C equal to small c. Then this probability, that is B given C. So B is again C equal to small c given A equal to 1, B equal to 1. Now the issue with this is you cannot compute these probabilities. This is difficult to, I mean, we don't have access to these probabilities with us. That's the problem.
Okay, so that is why we just ignore that C condition only, and we just use only A and B.
Huh. See, there's no ignoring, Bhavani. So the point is, this statement is equal to this statement from trivial, conditioning formula, right? Now the point is, when you have all of this, because we assume a naive-Bayes model, this probability becomes easier to calculate. This also becomes easier to calculate. That's it. So there's no business of C coming here. But if you want C, let's say if you have some model of C also, you can use it in this form. That's the idea. Is that clear?
Yes, sir. Yeah, kind of. But because why I consider C here is, I know based on Bayes formula, whatever is the second formula is correct. But given that table, so it means K's values depending on A, B, and C. So that is why I thought I have to sum it on all C. So
Right.
that is how I was thinking.
Correct. So I get the confusion, but so that's the point we make in naive Bayes, right? Because so once we come in this particular formulation where I'm conditioning on the class, features become independent. So that is the best. I mean that's what we have with us. So when that happens, then it becomes a simple model.
Sir, can you go to previous writing, sir? You return the probability of just previous one. Yeah, wait, sir. Here it is. See, the confusion why you are writing like probability of AB given C, okay? And
right.
That means in our case here, K equal to 0. And see, let's see, basically this is actually the expected output. No? So why we are writing in the B, what is C is the input basically, right? The input feature is not the class label basically. So
Correct.
why, so how it, if you're getting the exact idea of this one, I think we'll get clarity on the other one.
No, see, okay. I mean, I understand. See, okay, fine. You're right that we use A, B, and C to make inference about K. The point is all of these are random variables, so I can always have a joint probability distribution. So right now, what I'm looking at this probability distribution is just the joint between two variables, K and P, conditioned on two other variables. That's it. Now, how do you use for inference is this exactly this sort of idea. So where you're saying, okay, I have only A and B with me. I know what A and B are. Can you tell me what the probability of K being 0 will be? You can answer that using naive-Bayes assumptions through this sort of a scenario. That's the idea, Satish. Does that make sense?
Okay. Sir, that one more thing that the input features are we have independent. No? The C is independent of A and B. See, K is dependent. The K is dependent, correct? But C is independent of A and B, am I right?
C is independent of A and B only on conditioned on class, only on condition on K.
Okay.
Otherwise, they are not. Yeah,
okay.
yeah.
Okay. Clear.
Probability, yeah. So probability of feature, let's say A and B are features. Only on class they become this A given K into P of B given K. This is the naive-Bayes assumption. Basically, see, because the idea is this probability is also not easy to compute. So we make an assumption that okay, given the class features are independent, then you do this. You just get a multiplication of terms. It becomes easier. All right. Okay. Any other questions?
Sir, in week 3,
Week 3.
lecture notes, sir, might be if we can open our lecture notes.
Yeah, yeah. Go ahead.
Page 9, sir.
9. Okay.
Is that? No,
Is this
9. Week 3 only, right, sir? No, I see. Wait 1 second, sir. Let me also open because I just noted it. Okay, yeah, here, the before page. So first, so the last sentence, sir, here. So as training set approaches infinity and k grows large, kn becomes base optimal. What does this mean, sir? Like, how couldn't understand this?
So base optimal is it has to do with this exactly this sort of formulation where you say what is best probability that you can get with some errors and everything. So again, these are some proofs which I have not done in a long time, so I don't remember clearly, but not sure. So I won't be the right person to answer this right now at least.
Okay, sir, no problem. But if we go down, sir, a little more, page 11 or little more. Yeah, this diagram. So here they compare about KNN being used with training error and validation error. But as per my understanding, KNN directly we use on test data. So we don't have really a training phase in KNN. So how are they really calculating this training error and tenfold cross validation error for this KNN algorithm?
For KNN, is it? No. So
Right.
how do you get training error for any algorithm? You just pass that same example back, right?
Can you repeat, sir?
So how do you get training error in general systems, right? So let's say you have a model, which is let's say some trained model or whatever. How do you get the training error? You pass the training examples again back into the model, no? And you check how much what is the predicted let's say training label versus the actual training label, right? Yeah, actual training label. So same thing you do with so in KNN there's no training phase, but I can always pass the training data into the model as a test example and get
But there is no training data like only, right, sir? But it's all are like so when you're saying training data in the KNN, it means like okay, all those data points with the class labels, and the new unseen data is the test data. So that is what you're saying. Okay, and we can just kind of hide the class label for one of the training data and see how it works. Is that what? Okay, got it.
So you just basically run the training data also as like test on the model and get the predictions for the training label. Compare that with the true label that we have. That's it. That's the training
But
error.
I don't see any difference between that doing that with see I'm just telling training data, but it is the same as doing test only, right, sir? It's not like it's actually test error only. So we are not really doing any training kind of thing. So I can still consider that data as my test data, and because I'm doing the same thing in both cases. Even for test data, I'm like taking that data and just finding out the neighbors and then trying to see if that accuracy is.
No. See. The point is in KNN, how are you getting the final label? You need some data to get the label back, right? So let's say if you have three classes like this. Okay, now let's say I have a new point here. Okay, now if the label for this question mark is let's let's say plus and opposite, plus and circle are your cross mark are your points labels. So if the true label for this question mark was plus, right, then you will not be able to get that from this, right? If I use 3 nearest neighbor versus, let's say, if this point was given to you. So basically, is this point present in the training data or not? That will influence how your prediction is changing, right? So it is not exactly, see, we are not training anything, doesn't mean that there's no difference between the training and the test data set in KNN. I hope you got the difference, Giovanni.
Sir,
Yeah, I got, sir. Only what I means, but still little not
sir, I
completely
can answer,
clear.
sir.
Sorry, who is that?
Satish, sir. Can I answer?
Go ahead, Satish, go ahead.
Sir, actually, this question I asked last time, so I got understood what the explanation given by. I got clarification. What is the idea here, basically? See, it is actually a non-parameter, so we are not calculating the parameter. This is called lazy learning. That doesn't mean that no, we have the training phase, we have the test phase. We have to finalize the value of k. I bet voice there is some disturbance is there. I think it's audible now.
Yeah, go ahead.
Yeah, so we have to finalize the value, what is the best k value and what is the best distance algorithm. So we will train with the initial some testing data, sorry, training data, and you have to keep some testing data separately. Train it and you will finalize one k value and your distance algorithm. Now you have to see that unseen data, how it works. Based on that, again, you will go back and train it to best select the k and distance algorithm. Okay. So how to fine tune it? The fine tune is having testing data only. So we have the testing phase, we have the training phase. Only thing is we don't generate the parameter, that theta and whatever. It is there k and k value and distance algorithm you have to finalize. For that you have the two phases. Is it clear now?
So Satish, I'll modify that. So it's not training and testing; it's training and validation.
Yeah. Sorry, validation. Exactly, validation. I mean testing is validation here.
Training, validation, training, validation, and test. So validation
Yes,
you will use to understand what's the right
yes.
K, what's the right
Yes.
distance metric. So I
Yes.
think Bhavani's question is more involved in the sense that, let's say, okay, you get something from here. Now the question is, how are training and test different? See, Bhavani, they are different because of this fact that, let's say for this particular example, if this point was given in your training set versus that being a point in your test set, that makes a huge difference, right? So that is what is the difference between the training and testing here. All right.
Okay. I kind of understand there is actually not a training phase for parameter calculation, but still we need a training phase for computing the value of k, the optimal value of k.
Correct.
Right, sir?
So you'll
Okay.
have
So
the
that is.
validation set. Yeah.
And
What
I
you will
remember the test will give you the final true error, so that we will not again fine tune it. It will give to us what is the final performance, accuracy, and recall. All will calculate on the test data.
That is true. That is true. So, let's say you have some training data set for your KNN. You'll also have some validation data set. So you'll pass the validation data set through the model, your KNN model, get the labels, see the error, and then fine tune your K distance measures, all of that. That's how you'll fine tune this KNN models, and then finally you will do it on test. And as Satish said, then you will report all your things like F score and precision and all of that. Right?
Okay. Got it. Thank you.
Jiten, what's your question, Jiten? Error, once again, Bhavani. So, error is sum of training plus testing or training plus validation. Which error you're talking about? Which question is this? Is Jitendra here? In general, error in ML means so in general, error means test error. That is it. We only care about the test error because that's the true way of. I mean, that's the measure of how general the model is, right? Validation error also, we don't generally take it as this one, because you're using that to change the model at the end of the day, right? And training error, obviously not, right? So when you say, let's say somebody comes and tells you what is the error of your model, they mean the test error, unless they are specifying, okay, what's the training error, what's the validation error, and so on. Okay. Is that clear, Jitendra? Okay. Yeah, go ahead, Bhavani. You had a question?
So in the same lecture note, sir, if we scroll down the week 3,
Week
so
3.
little bit. So here there is this one, sir. So there is something called, they say, kernel width. So kernel width controls. I could understand the weighted with distance. So it's either distance or it can be kernel width, they say. So what is this exactly, kernel width, sir?
So we discussed this last time, no? So I would say, go ahead and go through this one. So do you have any questions on that though?
On which, okay, so this one we discussed is in SVM, sir, the kernels. So that one was different, but here it is.
So here also we discussed last time, no? Satish, do you remember?
Okay.
I remember we discussed that to shape the shape of the things, no, the smooth turn and all things. I remember. I don't remember you or other TA, but it was discussed. Yes.
So let's say you have
no
point
problem.
P1, point P2, and kernel width basically controls how much importance you're giving to point P2, the distance between point P1 and P2. So let's say this is, let's say, something like this versus something like this, right? And versus something like this, right? So the idea is, so how much does this distance compare with respect to this different values? So if it is very small kernel width, then what will happen is these large distances will shrink very quickly. So you're looking at very close neighborhood of your point, versus when you have larger kernel width, you're looking at a larger space. So points which are of more distance also will have a control over what your final output is, and so on. And kernel width is also a hyperparameter. You generally tune that with validation set. Okay. Any other questions?
Sir, okay. If there's no questions, I'll ask. If anybody is there, let them go ahead.
I don't think. Go ahead, Satish.
Sir, there is one small clarification. This is discussed, I think, twice. Okay, once I discussed, again, I think Bhavani also last time asked the item-based collaborative filtering. Okay, so there's a question came in the assignment. I think there's 3 only, that KN and all it comes. Can you open, sir, actually?
Collaborative filtering is here only. Yeah.
In assignment.
No, I remember the question. Go ahead. What was the?
Yeah, see, collaborative filtering as the 2 method was there. One is the user-based, and second one is the item-based. Okay. Now, item-based was considered as a similar user and similar item basically. Okay. So answer is finally given the similar user, not similar items basically. Okay. Now, and at time, I think I discussed the other tutor also once with you, Bhavani discussed, I remember. So the other tutor is not given, it's okay, because that one slide I shown, it's clearly told that the collaboration filtering is similar item is part of collaboration filtering. Okay, in one slide in the class actually, there's one part. Okay, the second part I have one small doubt that day you are explaining to us actually for Bhavani question. So it is not the user or it is basically the similar item is how you make a similar item. That's the question came. So similar item based on the features of the item. Okay, so similar item can be done on the feature of the item. That's one method of doing. That is not part of collaborative filtering. In collaborative filtering, basically similar item means it is basically how the users are. This is the item, not item features actually. It is basically how the users are use that item. That means if I do the row and column arrangement, this item finally the one item is there. All users are given some rank for it or some value is given, credit score is given. Now the next user going to buy it actually. So it is compared with this item, how similar to other items in the ratio of their scoring. So it is like a collaborative filtering only because coming that part. So the data it's okay. It's told like feature similarity. Feature similarity is there, but this is not a feature similarity. It is based on the similarity of the how the user rated. Then it is a CF or not CF. I got confused now.
So
You got my point.
So content based recommendation, whatever is there, that is similar items. Here, so similar items means similar features. That's it, right? So and as we discussed last time, let's say if you're talking about movies, genre or plot details, all of those are features of a movie, right? How do you characterize a movie?
No.
Collaborative filtering.
My question is, suppose I don't use the feature to identify the similar items. Another approach is basically the rating of the people to the same item. That approach is also there. I think in the class also, madam told there is two methods there. Either mostly we'll use the similar user only, but the number of users are very large. If number of users are very large, instead of going to the similar users, we'll go to similar item where we don't see the content, we don't see the features. Basically, we will compare the rating of the similar item. That means the user goes to one item, the same item, how the other people are rated. With that average value, we'll buy it.
Okay.
Then it is not a content-based filtering. It's a collaborative filtering only, no, sir, because we don't see the content actually.
Yes. So hence it's a collaborative filtering. It's not a content-based recommendation.
Then in this question, in collaborative filtering, the items recommended based on what? Similar user, similar item. So both of above, both none of. So both of above, no, sir. We can recommendation can be done similar user, similar item, no.
No. So see again. So mentioning that in the option when it's given, they give similar item here, it means content-based similarity of two items. Because see, at the end, in your collaborative filtering, when we looked at items also, at the end it was user rating, right? Which you use to define the similarity of items. So at the end it comes to users. So that's define and you say that okay, collaborative filtering is only similar users. Is that clear?
Sir, but in the ma'am's notes, sir, content based is not called as collaborative filtering, sir. It is called content based recommendation. Two types of recommendation. Content based. Hello.
Sorry, yeah, go ahead.
Okay. So there are two types of recommendation, which I think ma'am explained. Is one is content based recommendation, other is collaborative filtering based recommendation. So in content based recommendation, what you're saying is like, okay, based on if for the user, they might check the old products and then they might recommend the new products. It is the same user's content. They don't check with other users. So that is content based recommendation. But here collaboration doesn't come into picture. So whenever ma'am explained about collaborative filtering, that time she explained about both, sir. She told similar users and similar items. So similar users, she told, okay, practically it is not possible because of the huge number of users. So that is why we kind of consider similar items. Even when I was looking after your answers, I was looking in Google also, but they kind of gave both, sir, like similar user collaborative filtering and similar item based collaborative filtering. So that is why I'm like, I wasn't little convinced why exactly here the answer is different, but the explanations are little different.
And one more thing, sir. One more thing, sir. In summary of features, what I understood, when we tell the content content-based filtering means we will go to the features. For example, if I take the movie, who is the director, who is the audio, or who is the actors. So we will see that the person next. So we will see the same person data. The person's last time what is seen, whether it's which movie you select, what type of movie you select. So there you go the content based. But when collaboration means we don't use the same features of the for the same customer. We see the how the other customer is recommended or other similar item with the other customers. That means if users want to, that way it is.
So okay, so 1 second. So to put a rest to all of this, 9B, the option number B in the question number 9, similar items. Here, similar items means content-based similarity. So now tell me, will 9B be a right answer for this question?
Can you repeat, sir, your question?
So 9B, the option number B in question number 9, similar items means content-based similarity. Okay. Now, if that's the case, is 9B the right option?
If it is content-based similarity, then no, sir.
No, right. Okay. Now let me clarify. When they say similar items, it means content-based. So similar items for collaborative filtering came up again. You use it only you use the ratings, which is again just only the user-driven system. All right. So hence, it's not the right option. That's the idea.
Sir, that I have one small this one. Whenever it comes to us now, in general, if they don't tell CF based similar items, we should think about is the content based similar items. Am I right? Like that, I can think.
Yes, content based.
If they tell clearly it's a CF based, that means no, that collaborative. CF means usually I tell collaborative filtering. So it's a collaborative based similar item means I can go for is collaborative. If simply they given similar items, it's understood implied that it is the content based similar items.
Content based similarity, yes.
Similar items that we should look into.
Yeah.
So if they might have given here similar items of same user, then we understood clearly it is understood, sir. Here similar items given, similar items of same user, then it is clearly it's a content based. Then we don't have any confusion there. Since it's given only word similar items, is it similar items of same user or similar items across the users? We are not very clear. Similar items across the user, then it's called collaborative filtering. Similar item of the same user, it is a content based filtering. That is a more understanding for me.
Right. I understand, and agree.
I think Satish put that that doubt in a very good way, sir. Because similar items means if it is of same user, it is content based. Otherwise, it is possible even for different users. Then it will become collaborative filtering. Okay, but here that confusion was there.
Now it is in general. In general, maybe in the machine learning terminology, similar items means it is understood as a content based. We should think like that. In general.
Yes. In general, yes. That's how you will use it. Yeah. So Arya, I got your point. So in 2019 run, apparently they gave the question number. So option number C was given, is it? So again, so I've confirmed this with the TAs also this time. So we all agree that, I mean, the A option is the right one. So this run, it's option A is the one that we have.
Okay, sir, in that same lecture notes, lecture 3, if we go to the last page, sir. Oh, no, sorry, it is not lecture 3, it is lecture 2.
Lecture 2. Yeah, in this last page, is it?
Yeah, go till the end, sir.
Go ahead.
Okay, little scroll up, sir. One, 2 slides up. Yeah, here, this dealing with overfitting. So they explain like we can use more data, use a tuning set, regularization, could understand, but be a Bayesian. I was thinking, how come Bayesian can handle overfitting?
So this is actually a bit advanced concept. So I'll just mention it what we do. So Bayesian neural networks at least. I want to give. Okay, fine. So the idea is this. So let's say you have some. Let's not do this. Yeah. So let's say you have some. So Bayesian in the sense, the idea is, let's say you have some parameters, right? Let's say P is a parameter set of your model, right? For let's say, for example, let's say in KNN you have K is your parameter, right? Sorry, hyperparameter. And then let's say in case of neural networks, you have those weights that you have as parameters. So the idea is in Bayesian, what we do is we assume a, let's say, I'll use a different theta. Let's say theta is a parameter set, right? So then what you do is currently the way to solve in this way is you just try to look at the what is the maximum likelihood estimate of this parameter set theta. In Bayesian approaches, what we do is we assume a prior over the parameter set itself, right? And then we look at the posterior given the data. So this is how you solve for that problem. Probability of D like this. So why would it help in regularization? Is basically you're posing some constraints on the way your theta, your prior should be, right? Based on previous knowledge or just your hunch or whatever, right? So this makes sure that the amount of space that the model can the parameter space that the model can go through is a bit restricted, and hence you are trying to you basically having a control on the overfitting problem, because in overfitting the idea is all those parameters are free to roam wherever they want. By imposing a prior on them, you're saying okay, some values are more likely than the others, so the model has to look at in that particular sort of space only. So hence it helps in sort of this overfitting by being a Bayesian. That's the idea.
Okay, sir, understood. This and using a tuning set is nothing but a validation set. Is that right, sir?
Validation. Yes.
Validation. Okay.
Validation set.
Okay, sir.
How should we deal with such language issues in the exam if words are used with a more restricted meaning? See, again, I would say get those questions out and you can ask it on the forum. We discussed this last time also. So otherwise, I mean, I have no other solution that I can see here. And yeah, that's it. That's it I have with me actually. Solution for that.
Sir, this is actually, yeah.
Okay, next question. Anybody else? Any other questions?
Sir,
Go ahead.
yeah, this is just for my understanding purpose. Out
Yeah.
of 8 modules, we learned different 8 topics, like starting from the linear regression with the decision tree. Then we have KNN methods. Then we have the Bayesian. Then support vector machine, neural network. Then computer learning theory. Then finally clustering. As per what is the difficulty level of the each topic, which is the most difficulty, so that it will help us because, for example, why I'm asking this question, I am seeing this after a long time. I was a working person, so whether my complexity or some time I think it's difficult, little bit difficult. I'm not any complete difficult. The course is not very difficult, yes, basically, but some topic, like some of the topic I feel is difficult, little bit. So if you're in your things, in your suggestion, these are topics more easy than whatever you are rating. Is there you can able to give?
Satish, again, I think I answered this long time back also. There, the whole point of saying difficult, not difficult is a very, very personal choice. It's for example, now for me, this Bayesian neural networks, I still have trouble trying to understand things. I mean, trying to do things. But let's say in case of machine learning, the neural networks, because I work with neural networks very regularly. So I'm in tune with all the kind of issues that exist and what solutions are people are doing and all of that. So no, I refuse to comment on what is more difficult and what is more likely to come and all of those kind of things. If there are questions regarding some concepts, please ask them. Let's make sure. So we have 25 more minutes. Any questions on that? Let's tackle those things.
Thank you, sir.
Can you explain dendrogram questions, sir, in week 8?
Week 8, okay.
Dendrogram diagrams.
So, okay, so what is unclear here?
Sir, can you elaborate that, sir, and explain some brief, sir?
So how do you form the dendrogram?
Yes, sir, and how to solve that one, sir?
So, so Pawan, did you join late or something? Because we covered this question. Yeah. So I mean, again, this question, for example, the idea is if you draw a horizontal line, the number of vertical bars it cuts, that's the number of clusters it will be formed. Again, the idea is, so we are sort of saying, okay, I want clusters which have maximum, this whatever the metric is on the y-axis, which have that metric to be only this 2, for example, right? So we 2 or less than 2. So hence we say, okay, this is one cluster, and this is another cluster. A, B will become one cluster, and C, D, E, F will become one cluster. And how do you form dendrograms? So that you can look at the way you do clustering, hierarchical clustering, right? So in hierarchical clustering, the idea is you look at let's say, so you say all the points are their individual clusters, and then you look at each of those points pairwise distances with each other, right? And whichever has the smallest distance, you cluster them first, and then go on like that, right? So that process is represented as a dendrogram. So for example, let's say 1, 2, and 3 are here. So so 1, 2, 3 is the sample numbers are given here, right? So let's say if you first cluster 2 and 3, that becomes the first box here. Now, okay, in this case, so let's say we have another point, let's say at somewhere here, right? 4. So now we see, okay, 1 is more closer to the cluster that is newly formed, 2 and 3 compared to 4. So this becomes the next cluster, and then only 4 is remaining. So this becomes the next cluster. This is how you do it. And then you have things of how do you compute inter-cluster distances and all of that. So if you have anything more specific, let's tackle that.
Yes, sir. No, clear, sir.
Hello, sir. I have a question. This support vector concept of classification, actually, if we go through that concept, it appears to me the learning in the support vectors is nothing but if you are able to identify 2 support vectors, and then we can arrive at the margin. So actually, it is the process of learning is nothing but discovering the support vectors, right? Which maximizes that margin.
Yes. So maximizing the margin that you get, right? So this can be posed. So I think I mentioned this, I don't remember, but maximizing margin is a primal problem. And if you look at it, it's the dual formulation is basically trying to look at which points are support vectors. That's it.
Yes. So the whole learning is discovering the support vectors. Yes.
Support vectors, right. So if you are able to get which points are support vectors, you can actually recover the margin, the plane also, and so therefore it's equivalent. Both these things are equivalent. So if you get support vectors, then
yeah. And there is another point regarding SVM is that it can work with small data sets, right? Small training data sets as well, easily.
See, again, easily and all, I'm not sure. But the point is, any algorithm for that matter can work with small data points. It's about how it performs on test. So that is something that we cannot say about any algorithm in general. Gopal Krishna.
Okay, sir.
Sir, regarding this SVM, maybe we'll find the nearest points, right, sir, for the margin. So in case for in the same line, if we have like 3-4 points, all those 3-4 points are considered support vectors, or any one is chosen on that margin line?
No. So not all are considered. So basically, what ends up happening is, let's say you have something like this. Let's say this is a margin, right? Now, let's say if you have uh, points like this, right? Now, because of the fact that so let's say these 2 points both lying on this margin, both won't be considered as support vectors. So this is actually a very special case in the support vector machine theory. What will end up happening is this will have this one of them will become a support vector. The other one will not be considered as a support vector, because if I remove this point also, the margin is still remaining the same. So ideally speaking, so therefore it doesn't contribute as a support vector. Only one of them will be used, and which one of them will be used is depends on how the algorithm has progressed. It's very there's no deterministic rule as such to choose among the different points.
Okay, sir. But will it give the result like which one it is considering a support vector?
Yes.
Like
Yes.
might be if there are 2 points. Okay.
Yes. Yeah. So you will basically get some. Again, if you go to the dual formulation, you will get something called as the Lagrange multipliers basically. So wherever those multipliers are non-zero, they are support vectors. So for you'll actually see it happening that it'll become zero for this and it'll be non-zero for this. Whichever is non-zero, that's taken as support vectors.
Okay, sir.
In decision tree, if more attributes are present, we need to calculate information gain, and based on that, prediction will be done. Is there any short method for prediction? See, prediction is very straightforward, no? In decision tree, Devika. Decision tree, once you form the decision tree, for example, let's say some attribute, let's say a less than 2 and a greater than 2, a greater than 2, and then let's say here we have b equal to some true and b equal to false, right? So yeah, so what will end up happening is, let's say you have a sample which is, let's say a equal to 3 and b equal to, let's say, false. You will just go through the decision tree. So we'll say, okay, this branch, then again this branch, and then whatever the prediction is here, it's what you will use, Devika. So the prediction is very fast in decision trees. So I'm not sure what do you mean by short method for prediction. Nothing can be shorter than traversing one branch of a tree. What will be the ideal complexity of the curve which can be used? Again, this is discussed in the previous week assignments. Please go through that.
Sir, another
Devika,
question.
One second, Gopal Krishna. One second, Gopal Krishna. So, Devika, if you have something, just type it again, okay? Go ahead, Gopal Krishna.
Yeah, and in logistic regression, the activation functions are there are three kinds. One is a sigmoid function, which is commonly used, and tan h and ReLU. Okay, which one is used in what context? Normally, we use sigmoid, I know, but when do we use tan h and when do we use ReLU?
No. So, logistic regression, you only use sigmoid. Tan H, where do you use in logistic regression?
Oh, tan h we use. Oh, sorry, we use a neural network only, right?
Neural networks. Neural networks have tan H, ReLU, and all of that. And see, logistic regression also you can do it because see, tan H and sigmoid are very closely linked, by the way. But but the idea is sigmoid is used for logistic regression because you want a probability, right? So that probability is given by that sigmoid function, 0 to 1 always, right? That's why we use the sigmoid. One reasoning is for which is sigmoid is that.
Okay,
Got it?
but ReLU is most common used in neural networks, right? For calculating backpropagation, it is easy. ReLU, is it correct?
So again, so easy and all is not a good way of putting things. But ReLU became famous for CN networks. So let's say in convolutional neural networks, the first sort of neural network which could do something better than the basic algorithms was one where they used ReLU as an activation function. Okay, and ReLU is not the God activation function as such. So even ReLU has some issues, and there are many others which came after that. There was in the same pronunciation, you have something called as CeLU, you have ELU, you have GELU, and there are many others like that.
Yeah.
Ha.
So actually in neural networks, it is the activation function which actually brings non-linearity, right? Otherwise everything is the linear algebra, except the ReLU function where it converts a linear into a non-linear. So intuitively I feel that it is activation function which actually gives life to
neural networks. Yeah.
Non-linear behavior to the neural networks, correct? Yeah.
Yes, precisely. Yes.
So for this ReLU, it is still if it is x is greater than 0, it is still linear only, right, sir? Only for x less than 0, it is still a straight line. So it is linear in two different paths. So it is still linear in x greater than 0, and it's also linear in x lesser than 0. So if we both combine together, then
so
it
such
is
functions have a name called piecewise linear.
Okay.
Yeah, they are called piecewise linear functions, which are not linear at the end of the day, because again we discussed this also. Linear function means they have to satisfy this condition.
Right. Okay.
Right, for all x, a, b. Yeah. So ReLU will not satisfy for some cases, and therefore it's not linear as such. It's a piecewise linear function.
Okay.
Sir, so another terminology confusion, the concept and hypothesis. Sometimes we use these words interchangeably. Can you just elaborate the distinction, the terminology? When do we use concept? When do we use hypothesis?
Yeah. So this is, for me also, this is
Okay, hypothesis I understand intuitively, but concept means one hypothesis we call as a concept, or no?
No. So hypothesis is basically a function which classifies 2 points or whatever, right? That's the hypothesis. Hypothesis space is all those possible functions.
Yes.
So concept is this subset of objects from the X. So here, see, what is the X? X is basically the feature space, right? So basically some collection of some subset of this feature space objects. That is a concept. So let's say, for example, let's say you're trying to do let's say 2-class classification problem, right? So now these 8 points are actually lying in this R2 space, right? A 2-dimensional space. Now these 4 points is one concept. Any subset you take. Now the point is concept is a bit more important, because we're saying, okay, all of this belong to some one type of points. So that becomes a concept. That's the idea. And this is another concept. And
basically, it is a subset of the data set, right?
Subset of the data set, yes. Data set, but only the feature space. We're not considering the labels here, but labels are used to understand. So labels are used to understand which subset to use. That's it. That's the end of the label. But the concept is basically the elements in that the feature space. One subset in that.
Okay.
Yeah.
Sir, can CNNs be used for regression also?
Yes. Let's say you have something like mm, yeah. So let's say in an image, right? You have an image, and let's say you have some object here and some other object here, right? And you want to know the distance between them, right? Now the point is that again, for many problem statements, for many image based problems, CNN seem to work better. So then what you can do is you will have like a set of such images, and you'll have a output will be a real number, right? Because you want a distance, let's say in pixel space, for example, like distance in the pixel space. So that becomes a regression problem, right?
So if I have image data as well as numerical data, like the lab findings or something like that, can CNNs be used for that purpose?
I'm sorry, it wasn't clear. What data you have? Image and?
So if I have an X-ray data, like an image data,
okay,
along with that, I have some lab findings data, which is basically the numerical data.
Okay. Lab finding. Okay, yeah, got it. Okay.
So
how
can
can
CNNs be used for such tasks? Yes, sir.
Yeah. So all of these are basically these multimodal sort of networks that exist. So basically, let's say when you have data modality coming from multiple different modalities, right? So then what people do in such things, one way of doing things is you have a CNN, let's say which takes the image as the input. And if you remember CNN, we have multiple different small layers, right? So convolution, then you have that max pool or average pool, some pooling layers and all of that. So what people do is you have these sort of some layers at uh, some number of layers, and then you have a flattening layer, right? After the flattening layer, now it has become one vector. Now what you will do is you will append your lab findings data, because these are all just real numbers. Let's say you have two data, some X and Y something, right? So X becomes here, Y becomes here, and then all of this goes into the feed forward network. Some feed forward network which predicts some output here. So all of these weights which are there, they will be used in this format, and image will be passed through CNN. This is one way of doing things.
Okay, sir. Fine. Thank you.
Sir, can we use neural networks for clustering, sir? Clustering.
Yeah, there's actually a lot of work in that. I'm actually not completely aware of it also. There's something called as I think self-organizing maps or something like that. Again, it's been a while. They sort of I think these use neural networks for clustering ideas. So again, see, the point is in neural networks. Yeah.
So far, we discussed only
So there is
supervised
something
learning.
like that. Sorry.
So far, we discussed only supervised learning, right? In the context of neural network, only supervised.
Yes. Yes. No. So we also discussed so clustering, no, but unsupervised learning we did, right?
Example.
Because autoencoders.
Autoencoders.
Right.
Yeah,
because the idea was
they are encoders, right? They are not actually clustering. Okay, no. Yeah.
It's not clustering. Exactly. So unsupervised learning, we have neural networks being used. Clustering also there, but there's a completely different field of the work, and I don't really know much in detail about that also. So I won't be the right person to answer this. But go ahead and check out the online what comes up on this.
Hello, sir.
Yeah, go ahead.
So the previous image you have shown about the multimodal thing, right?
Yeah.
This X and Y is a dependent and independent vector, right? No, this
I'm
is
sorry,
X and Y. That X and Y you mentioned, right? This lab findings, some X and Y data you have represented, right? So the X and Y is nothing but whatever the vector you consider as a dependent vector and independent vector, right?
Oh no, sorry, not that X and Y, no.
Okay.
So let's say some feature 1, feature 2, finding 1, finding 2. That is what I meant.
Okay, I have a question here. So lab findings, suppose you are considering some non-clinical data set, some record you have, some patient's details, okay?
Okay.
So various features of the patients, just like that. So you have number of features. So you are creating, suppose finally you are going to classify in terms of binary classification, okay? Some yes or no type, whether the person has some kind of disease or not, okay? So you have the binary classification at the end of the output. So you have so many features like F1, F2, like Fn till Fn, okay? So you will finally set independent and dependent vectors, okay? So this F1, F2 is nothing but your independent vectors, right? Right?
Yes, because you're using that to predict the label, no? So this becomes independent. This one variable, and these are called dependent variable. Yeah.
Okay, so this is one mode. Then another one is the images, right?
Yeah. So you can use image also. Yeah.
Image also. So you are going to analyze in terms of multimodal thing, right? So finally you have to take the decision, right? So the decision making, how will you do it?
Okay, let me ask you, how will you do it? So we have done machine learning for 8 weeks now. How would you do decision? So
that is so many decision.
What all do you need to?
The fusion decision. I'm not sure about all those things. No, when we combine this data findings, the lab findings and image, both are in different characteristics, right? So
Correct.
how will you make the decision in the output side?
No, but so what is the decision that you want to make? You want to make whether the person has, let's say, some disease or not, right? So when you have,
so the same manner, the image is also some kind of see, for example, some cancer, okay? Some cancer, some person having the cancerous or not, okay? So the corresponding lab findings data I have based on the person's features, okay? So I want to consider both the things. I want to consider in terms of multimodal thing. Then finally, I want to conclude that the person has cancer or not, right? That is my ultimate output. So the first one you have the lab finding. The second one you have some image features, right? So that is like cancerous cell images, like kind of scan images.
I got your point, Sankari. Go ahead. Yeah.
So finally, how will you conclude whether the person is having cancer or not? So you have to take some decision, right?
So let's say you have you take his scan.
Can I answer this question based on my understanding? Suppose the neural network input has an image and also some numerical real valued inputs. So the output, desired output is whether the person has a cancer or not. Okay.
Yes.
So the image is processed through convolution layer. It extracts some feature, let us say it has a tumor or not, of the appropriate size or not. So that is one variable extracted. That is one input. The other input is some diagnostic laboratory report, the numerical input. Ultimately, at the end, it is only like a classification, only simple classification, 3 inputs. One input is coming from image extraction, like whether the image has tumor or not. The other 2 inputs are the lab inputs, which are normal real variables. So output is a probabilistic logistic regression.
Okay.
Is it no? Is it making sense, sir? Is it?
Yes.
Yes. No, finally I have seen some papers and all. They are using some decision, fusion, division, diffusion, something like that. Fusion.
What? Fusion.
Fusion method. FUSION.
Fusion.
Late fusion, something like that. No.
No, I'm not aware of that methods. No. Yeah.
Okay. Whatever he said, that is fine.
Yeah.
So finally, both are in vector format, right? So.
Right. That's the idea.
Yeah. Thank you.
Okay. Any last question?
Sir, one question. In the multi-layered network with the, in the neural network I'm telling, MNN, and with the deep, the basic difference, the feature extraction or any other can you that no multi-layer and the deep? See, in the deep again we have the convolution or RNN whatever. Okay. So the extra additional feature or one additional feature is the deep may always we will do the feature extraction in the beginning or it's all in convolution.
What feature extraction you're talking about?
In the convolution network, when you do it, the first phase we'll do it's called feature extraction. Then you'll do the finally classification. This one. When you can you open that slide, sir?
So I would say, I would say it's just a matter of convention, how you call it. That's it. See, at the end of the day, I understood your point. So CNN, you have like, you'll have some layers here, and then you'll say, okay, this is all feature extraction layers, and this is the classification layer.
Yes.
Huh. In normal MLP networks, if you have these sort of layers, right? And then you say, okay, this is the some output from here. So you can call these also as feature extractors, and this is called as a classification. Again, these are all very loosely terms that are loosely used. Don't worry too much about it.
Okay, then that multi-layer network and deep, how the different we will differentiate? Both are deep neural network and multi-layer network. How I differentiate?
No. So multi-layer networks are deep networks only. No, at the end, deep in this. So the word deep came about because what people were saying is we have too many layers, like not seen before. That too many hidden layers. That is
too
called
many
deep.
means I think more than one hidden layer means, sir. More than one hidden layer. Can we say it's deep network?
So no. So too many instances is like order of like 20s and very high, even more than that. Too many. That's what they are saying as deep. See, again, I would say these nomenclatures are very hazy. There is no clear cut. Okay, this is deep. This is not deep. Nothing like that. The idea is the same. You will train using back propagation. You will try to reduce the training error. That's it. Don't get hung up on those words, exact words.
Sir, just one general question. Are there any practical networks without back propagation, only feed forward?
No, but feed forward in a sense, but how will you optimize then? Because, how would you run that? Okay, the point is you want to learn the true function, right? Just remember the first class that we had. There's a true function, and we want to learn that true function. So without back propagating, how will you update your weights as such? Your initial guess, how do you know it's right or wrong?
Okay.
There are other ways of doing it also, though. So if you think about it, so there are other automation algorithms also. So
that means why we use the word feed forward networks? Because all neural networks have some kind of back propagation, right?
Yes, all networks have some kind of back propagation. So feed forward network is it's just that because of the way the connections are made, that's it. There's no much at least as far as I know, there's no real differences there. You can use different automation algorithms though. That's another way of talking about it. For example, you can use genetic algorithm. It's something called genetic algorithm to update to find the right weights, for example. Right. But the point is, what we are using currently is something which supports gradient based approaches. And for that, the backpropagation algorithm is one way that people see that we can use gradients to guide your search towards the optima that you have.
Okay.
Yeah.
Sir, are the terms cost function and loss function the same?
Yeah, it's you both are very similar. Cost function in very specific sort of algorithms, it makes sense to call them cost and all of that. But at least in a very general sense, cost function means loss function, because the idea is you tend to reduce the loss, which means you're reducing the which is also the terminology that saying reduce the cost associated with the prediction. there are very specific algorithms where there is, I mean, where you use cost by default. Otherwise, loss function is you can say it's equal to cost function.
Okay, sir. Thank you.
Okay, I guess we'll close the session now. All the best for your exam, and any other questions, just post it on the discussion forum, and either the course TS or you know I'll take a look. Yeah. So see you guys. Take care and all the best.
Thank you, sir.
Thank you so much, sir.
Thank you.